Okay, so this is the very first in our 3-course sequence on the introductory material for physical chemistry. And no better place to start than today's topic, which is energy and matter. Now, nature is the way it is because of energy and matter, and yet these deeply fundamental concepts are a little embarrassing in the sense that it's hard to put a definition on these things that doesn't sound circular. In a sense, there's a self-evident nature to these things. And so we can think of the matter as the stuff that everything in nature is made of, from rocks to fundamental particles to birds, whatever. And then energy is the thing that helps these particles, that allows these particles, these pieces of matter, to interact. Now, in actuality, energy and matter are really the same thing, and they can interconvert according to the famous equation of Einstein, E equals mc squared, where m is mass of the matter, E is energy, and c is the speed of light. So one could have energy that turns into matter, matter that turns into energy, and certainly that's very important. But at the level of chemistry, the conditions of chemistry, that doesn't happen. So matter stays as matter, energy stays as energy, and through much of what we will talk about in terms of physical chemistry, we can think separately about matter and energy. Now, when we study nuclear physics, which we won't do in this 3-course sequence, but we will later in the curriculum as we develop into physical chemists, the area of nuclear physics will indeed very much talk about converting matter to energy. We will make passing reference to it through this course, but we won't study it deeply. All right, well, let's talk about how we can think about building up the matter that we see around us. At the very fundamental level are the elementary particles, and they are characterized in our theory as through the Standard Model. Now, we will study the Standard Model later in the curriculum, but again, this is not in the scope of these introductory courses in physical chemistry. So the Standard Model deals with the fundamental particles and the forces between those fundamental particles. We will pick up our story at the atomic level. So the fundamental particles, electrons, quarks, come together to form atoms. Protons, protons and neutrons that sit within the nucleus, and then the electrons that surround that nucleus. The different way those nuclei are made up give us the different elements in the periodic table. And this is where we will begin our study with matter. Atoms then can come together in a whole variety of ways through chemical bonding to form molecules and compounds. The molecules and compounds then form the basis for building up larger structures. Mesoscopic, so several to tens of thousands to hundreds of thousands of atoms and molecules, to the bulk matter we see around us with Avogadro's number of atoms and molecules and compounds. And so what we study as physical chemists primarily is this range. And this is a massive range. One atom compared to Avogadro's number, 10 to the 23, is a vast order of magnitude. And so to truly understand chemistry, we have to understand things that are going on at the atomic and molecular level. The theories that we will talk about there are classical and quantum mechanics. We won't do a lot of quantum mechanics in this sequence, of course, but quantum mechanics will play a huge role throughout the curriculum. Then these come together in large quantities. This is the area of statistical mechanics. We will not also talk about statistical mechanics much in this introductory course, but it will be its own full course in our curriculum. And many of the related things to statistical mechanics will be their own courses. So understanding groups of molecules, or what are called ensembles of molecules, has its own challenges and needs its own theoretical framework, statistical mechanics. And finally, the macroscopic structures, the stuff that we can hold in our hands, the things we can mix together in beakers, is described at yet another level. And this is in the area of thermodynamics, which we will talk a good deal about in these sequence of courses. Not so much in this first course, but Introduction to Physical Chemistry 2 is a lot about thermodynamics. Kinetics also. So how fast do things happen? So we mix two things together. Will the reaction happen? And how fast the reaction happens are key questions that scientists ask. And so we will study kinetics as well. Now, everything we study in these three courses are going to be at the elementary level. So they'll be at the level of, say, a normal, regular general chemistry or physics, but with an eye towards becoming a physical chemist. And then we will cover some things that really aren't seen as much in general chemistry and general physics. So as you get through the three courses, I think you will have a good foundation in both chemistry and physics. And then we will launch into our deeper understanding of matter and energy. All right, well, the last thing I want to talk about today in this introductory course is the consequences of Noether's theorem. So Emma Noether, in the mid-1910s, so 1915, proved what's called Noether's theorem, published in 1917 or 18, something like that. And this is a very deep and profound theorem. One could argue that this is the most significant theorem in all of mathematical physics, and certainly could make a strong argument for that. And of course, we won't be able to talk about Noether's theorem in a rigorous detail in this course, but the consequences of this theorem will be pervasive throughout the course. Most of the time going unsaid, but I will try to come back to remind us of Noether's theorem when the opportunity is right. The crux of Noether's theorem is that she was able to prove that for any system, well, for conservative systems, but if the system is considered large enough, that's conservative, and we haven't given that a definition yet, but we will. Any continuous symmetry, or what's called an invariance, is associated with a conserved quantity. And the converse is true, vice versa. Any conserved quantity must be associated with an invariance or continuous symmetry. Now, we won't get into the technical details of what those continuous symmetries are. That's a very advanced area of mathematics called Lie groups and Lie algebra. But we can talk about it in sort of hand-wavy sense. So one invariance in physics is time. And to put it, very crudely, the physics we learn today is going to be the same as the physics tomorrow. So physics behaves the same today as tomorrow as it did yesterday. There's a time invariance to the laws of physics. Well, the conserved quantity associated with that is energy. And so the very storied and important theorem or law of conservation of energy is the partner to the invariance of time in physics. So conservation of energy is because of time invariance in physics, or the observation of conservation of energy must mean that physics is time invariant. There's a translational invariant. So the physics that I'm talking about here in Minnesota, and the physics that you're experience wherever you are, and the physics that's going on, if there's intelligent life out there and they're studying physics, they will be studying the same thing as we are. So there's a translation or positional invariance to the laws of physics. And that gives rise to the conserved quantity momentum. So the law of conservation of momentum is a consequence of translational symmetry or invariance. And finally, rotation. So again, here in Minnesota, if you're on the other side of the world watching this, and we're totally upside down from each other, we're rotated, the physics will be the same. And so there's a rotational invariance to the laws of physics, and the conserved quantity here is angular momentum. So the law of conservation of angular momentum is the partner to rotational invariance. Now, this of course cuts to the very depth of why nature works the way it is. So it's a very deep and powerful theorem, but it also is very, very practical. So a lot of problems that we will be able to solve very easily using concepts of conservation of energy and conservation of momentum and angular momentum wouldn't be there if we didn't have this theorem. And in fact, just thinking about collisions, what happens in collisions, the fact that we have to obey conservation of energy and conservation of momentum allows us to talk about collisions. And of course, the heart of chemistry are collisions. So Noether's theorem, a deep, deep theorem, but the consequences are extraordinarily practical. And again, I will try to remind us of this as we work through the course. But for now, I just wanted to bring this up on its own because of its importance. So I'm excited to launch into the first course here, and I hope you are too. And we'll see you in the next video where we do start studying matter and energy and the interaction of these particles and the energy that is given off and how that gives rise to all the interesting and fun things we learn about in physical chemistry.